Good morning, everyone. Let's wait a couple of more minutes until we start. All right, I think we can start. Um, I hope everybody can hear me. Um I'm recording this video, my screen, by using OBS Studio, and the recording of these lectures today will be available on YouTube unlisted, and I will post the links to these videos on odtuclass. These will be really high quality videos that you will be able to watch if you cannot make to one of these sessions. Um, so today, in the first hour, I'm going to talk about syllabus-related material. I'm going to talk about the materials we will be using in this course, the textbook, some additional material, and also how the assignments are going to be, the midterm final exam, things like that. So it will be syllabus-related material. And in the second hour, I'm going to talk about some geometric preliminaries that we will be needing throughout this semester if you want to implement the techniques we learn in this course. Our book does not contain these geometric preliminaries, and therefore I provided additional material for this, and I will be covering the first week and maybe part of the second week on this topic. If you have any questions during the lectures, please feel free to interrupt me. You can unmute your microphone and start talking. Don't hesitate to interrupt me, or you can write in the chat box. So right here, let me write in the chat box right here. Okay. If you have any questions, I will be checking the chat box from time to time. And I will also, when I post these videos on YouTube, I will also, in the description of the video, I will have an edited version of this chat transcript, which will just include course-related material. All right. So all these bye bye, see you later type of chats messages that we are going to have at the end of the lecture I'm going to delete those. Only course related material will remain in the chat transcript, and I will also upload it along with the video. All right, so chat box can be used for your questions. You can use your voice microphone, unmute yourself and ask your questions. Feel free to do it in any way you prefer. All right. So I will be sharing my screen, and I will be using PDF slides, and sometimes I will be drawing on GIMP. So I will be using this as a whiteboard. All right. And also after my offices, our building is currently being renovated, so I cannot use my office for these lectures. But after the building renovation is complete, I will be having these lectures in my office on my own desktop. But we will be using the same WebEx meetings. All right. So here is I will be sharing some course web pages from you from time to time. And here, so let's start today's syllabus related material. So the link to the course website is available on my personal web page under courses this semester. So every semester I update this section to have an up-to-date list of the courses I teach that semester. So this semester I'm teaching these two main courses. This third course is something that is really lightweight. I don't count it as a course. So these will be the courses that I teach this semester. And computational geometry has a designated course website apart from odtuclass. We will be using odtuclass mainly, but there is also material here on the course website. Especially there are three parts of this website, and this middle part, these are links. Sorry for the user interface, they don't look like links, but these are links that you can click. Schedule and course material, course homepage, announcements. I will be using odtuclass for announcements, so this third part is really is going to stay idle until the end of the semester. So, but this schedule and course material, if you don't have any access to odtuclass somehow, if odtuclass is down, you can use the schedule and course material website to access assignment descriptions, to access lecture slides, and this is it contains the tentative schedule of this semester. All right, so I'm going to go over this syllabus related material, and if you're just joined, if you can please mute your microphones. Yeah, I can actually do that. So yeah, I can mute you. So, but if you want to have any questions, please feel free to unmute yourself and interrupt me anytime. Okay. So I will go over this week by week syllabus today, but this is the course website that is independent of odtuclass that you can use to access lecture slides and assignment description. There's also the syllabus is also the course homepage. The first page of this, the landing page of this course website has the syllabus related information. It's out. We are not using Zoom. We will be using WebEx. The Zoom license, I think it's currently being purchased by the university, but I've been using WebEx in the last two courses that I gave, and I think it was nice. So I will be continuing. I will continue using WebEx. So right now we are in this lecture, Wednesdays. This is section 1. We will be meeting weekly on Wednesdays, but if you cannot make it to the Wednesday lecture, I will, section 2 is totally parallel with section 1. You can also attend the lectures one day before on Tuesday between 6 p.m. to 7 or 9 p.m. Usually I don't spend all the 3 hours lectures. Usually it's like 2 hours and 15 minutes. The second hour is longer than regular, but I don't usually make 3 hours. I probably will finish today around 11:50. No, yeah. In the second hour, for example, yeah, it will finish around 12. So I will probably finish around 12, close to 12 today. So the course is this course. So you may be wondering what we will be talking about in this computational geometry course. The name of the course contains geometry, but actually it's advanced data structures and algorithms course. We will be learning new algorithms, advanced algorithms, and we will also be learning advanced data structures we haven't seen before, like the segment trees, interval trees, trapezoidal maps. These are some data structures we will be learning in this course, and we will be learning algorithms like the plane sweep algorithm or randomized algorithms. We will design and analyze the talk about the complexities of these randomized algorithms. So it's really an advanced algorithms course. So there are no formal prerequisites to this course, but you need to have a basic understanding of data structures. For example, you need to know balanced binary trees. I will be talking about balanced binary trees, and if you really want to implement the techniques, algorithms we learn in this course, you need to be able to use, for example, the C++ STL, standard template library, the set or map data structure in there, or you should be able to use these balanced binary trees or other data structures easily in whatever language you're using. Okay, but I mean, these are for practice. We will the course itself will not do much implementation. Out of the 4 assignments I plan to give, one of them will be a programming assignment. The others will be writing assignments, written assignments, and so it's really a theoretical course. We will discuss the algorithms from a high level in pseudocode, and for example, if a balanced binary tree is used there, I will just say insert this to the tree, get this from the tree. What we will do is we will know that inserting and deleting from these trees is going to take log n amount of time. We are going to use them, discuss them in terms of complexities. Okay. So it's really a high-level theoretical course in that regard. But I also want you to experience the practice of implementing a computational geometry problem, solution to such a problem. So we will have one programming assignment. The textbook is a really classical textbook by Mark Deberg, Von Kravelt over Mars. The book's PDF is available. So this is the book. Mark Deberg, Otfried Chiong, Mark Von Kravelt, and Mark Overmars. So this is a really classical book, which I also used when I was a student of this course. But it's really good. It's not very easy to read in the sense that, as I said, it's really there are lots of theorems and proofs which will take some time to understand how those statements are made. So you need to really spend maybe like a half an hour sometimes to read a single page of this book. So it may be that from that regard it may be difficult to read, but otherwise it's a really well written book. We are going to cover at least half of the chapters in this book. So we will start with chapter 1, computational geometry, introduction, and our first hello world type of computational geometry problem will be the convex-hull problem. Convex-hull problem is a very standard problem which is actually covered in regular algorithms classes as well. We will see an algorithm named Graham's Can, but there are other versions of this algorithm as well. And then we will we will cover second chapter, and we will talk about line segment intersection problem. So if you think about these problems, for example, line segment intersection or point location, I'll just give 2 examples to tell you what computational geometry is about, what you should expect from this course. For example, point location and line segment intersection problem. Let me describe those problems one by one, and let's see what kind of a solution you will think about for these problems. Line segment intersection problem is very simple. It's like this. You are given a set of line segments on the 2D plane. So each line segment is given by 2 endpoints. We have the xy coordinates of beginning point, xy coordinates of the end point of the line segment. And we are given a bunch of line segments like this as input. Our goal will be to write a program to report intersecting line segments and the intersection points if they do intersect. Okay, so I mean, if I give you this problem, if you're new to computer science, you're new to algorithms, I mean, you just know programming, the only solution that you probably will come up and what you will think about is, okay, so this is, I want to find intersection between line segments. In terms of geometrical problem, this is not a very difficult problem. All I need to do is go over all pairs of line segments and check whether I need to write a function to check whether given 2 line segments intersect or not, and do this for every pair of line segments, right? I mean, in that regard, this problem is not difficult at all. But this is not a computational geometry solution to this problem. What we ask in computational geometry is the solution you provide optimal? Can you do better than that? So the algorithm that I described takes O(n) squared time. So can you do better than O(n) squared? And the solution is yes. In this chapter, we are going to see an O(n) log n algorithm to compute the line segment intersection problem in O(n) log n time. So that's a big improvement over n square. For example, if you have like if I give you 1 million line segments to check intersection, an O(n) square algorithm will take maybe minutes or maybe hours. It will depending on what kind of a system you use. But O(n) log n algorithm is just going to finish in seconds. So log n is a very slow growing function, and therefore O(n) log n is much closer to linear time O(n) than O(n) square. So we will see this is computational geometry is all about designing algorithms to solve certain geometric problems in the large scale. I mean, if you think about these problems in the small scale as geometric problems, they may not be interesting at all. But if you try to think about what happens if somebody gives you 10 million line segments, how can you report their intersections efficiently? By the way, you may also argue at this point, I mean, I expect some of you may interrupt me at this time saying that, oh, what if all the pairs of line segments intersect? Okay, that means that you cannot avoid spending O(n) squared time if all the line segments, all the pairs already intersect with each other. So in that regard, you will be right. If the number of intersections, let's call them, for example, k, if the k pairs of line segments intersect, k can be could be n square on the order of n square. So in that regard, you would be spending O(n) squared time anyways. But if you just develop an algorithm that is going to spend n squared time regardless of what k is, that's an inefficient algorithm. What I mean is that if k is on the order of n, O(n) for example, if only few of these line segments intersect, that's what happened in real life applications actually, then spending O(n) squared time regardless of that is not a good idea. Your algorithm is going to take long time regardless of the number of intersections, and that's bad. So we will have, when I say we will have an O(n) log n solution, our solution actually is going to be O(n) log n plus k, and it will be an output sensitive complexity. If the output is large, you're bound to spend more time. But if the output is small, if k is small, you will be bounded by n log n, which is going to be much smaller than O(n) square. So this kind of analysis that I'm right now making, I'm doing this just for you to understand what we will be doing throughout the course. We will talk about computational complexities of these algorithms that we describe. We are going to, so each of these parts, in the book, they are like theorems. For example, if I go to chapter 2, and after it describes the algorithm, so yeah, this is the algorithm. First of all, there are some lemmas in it. There will be theorems and lemmas. For example, this algorithm find intersection computes all intersection points and the segments that contain it correctly. So what does this lemma say? The algorithm that we propose is a correct algorithm. That's the first. So we will discuss correctness proofs. Is this algorithm correct? How can you prove it? And if you look at the proof, in terms of the mathematical proofs go, it's not very formal actually. If you look at this, it's just some English paragraphs that are written in the proof. All right. So the proofs will be high level like this, but regardless, they will still be proofs. If you read it, you will understand, okay, it considers all the cases, and it will be, when the proof is finished here, it will convince you that the algorithm works correctly. And here's another lemma. After the correctness proof, the running time of this algorithm find intersections is O(n) log n plus I log n. Actually, it's not. Actually I remembered it incorrect. I just told you that it's n log n plus k. Actually, it's n log n plus k log n. Okay, if this k is on the order of n squared, it will be n squared log n algorithm. All right, but usually this k, the output, is usually a very small number compared to, and it's on the order of n or even less than n. Therefore, we are going to have an n log n algorithm in general. Okay, so this lemma, for example, is a lemma about the computational complexity of the algorithm that is proposed, and it's proven like this in a like about a page. It proves that this complexity is correct. This is the time complexity. All right, so and every chapter is preceded by I mean the problem description. The problem is described formally, but there's in every chapter, every problem, there is an application, a motivating example that motivates the problem. For example, why do we need line segment intersection? And it motivates the problem by saying that in GIS applications, for example, you may have the road map, map of the roads in a country like this, and you may have the map of the rivers. So these two, the map of the road and map of the rivers, can be overlaid on top of each other to find, for example, bridges automatically. A bridge is somewhere where a road intersects with a river line. And also the way we represent these roads and rivers, as you can see, although they look like curved segments, they can be approximated by small line segments. So we can actually have these rivers as a bunch of small line segments, one after another. And when what a bridge is, an intersection of a river line segment with a road line segment, either in the midpoints or at the endpoints. The intersection can also be at the endpoints. But in any case, if you want to automatically identify bridges, you can actually you will have a problem which is related to line segment intersection. Okay, so every chapter is like this, and they're independent problems. You can read every chapter independently from the other. They do not follow. I mean, they may be from easiest to hardest problems, but not necessarily so. They are like independent problems by themselves. So which chapters are we going to cover from this? Yeah, here we are going to cover chapter 2. We are going to cover chapter 3, the polygon triangulation. Given an concave, simple concave polygon, we will try to solve this art gallery problem in which we try to find a minimum number of cameras to place on an art gallery so that all the art gallery is covered by these cameras. And this problem, actually finding the minimum number of cameras, is an NP complete problem. It will also talk about this, but we will be able to find an upper bound to the cameras that we place. For example, if you have an n-gon, a polygon with n vertices, if you're also, let me just show you this problem to motivate you what kind of a problem we will be dealing with. So this is the yeah, this is like an art gallery map. Let me zoom in. So by the way, the problems we'll be dealing with in this course are mostly, I think all of them are going to be two-dimensional problems. We're not going to talk about, for example, three-dimensional convex hulls or three-dimensional geometric processing techniques. Actually, such three-dimensional geometric problems are mostly dealt with in Yusuf Hocam's course, Geometry Processing, Digital Geometry Processing. So he has a course on digital geometry processing, and he basically deals with three-dimensional meshes. So in our course, Computational Geometry, we will be dealing with mostly two-dimensional problems. So in this art gallery problem, for example, we are given a simple polygon. This is a single polygon that you see here. It's concave. For example, this is a vertex, vertex, vertex. This is a concave polygon, not convex. But it's simple, meaning that there are no intersecting edges. There are no holes, so it's a simple polygon. Given such a simple polygon, the problem, art gallery problem, is how many cameras do you need to place? And each camera, assume that it sees 360 degrees around itself. But for example, this camera cannot see here because it doesn't have a clear line of sight to this point. So in order to see this, for example, in order to let me actually just copy this to GIMP, and I'm going to be drawing some things on it. For example, if this is my art, so what I'm saying is that this camera, if there's a point here, the line of sight from this camera to this point intersects some polygon edges, so this camera cannot see this point. So the art gallery problem, as you now understood, is the problem of placing the cameras in certain places such that the entire interior of the polygon is covered by the collection of these cameras. Two cameras may see the same point, it doesn't matter, but their union should be the entire interior of the polygon. So if this was a convex polygon, the answer would be just one camera. If one camera sees the entire interior of convex polygon. I will talk about what's a convex, what's a concave polygon later, but a convex polygon is, for example, a pentagon like this is a convex polygon. So if you place one camera, it will see everywhere inside it. So we are first going to prove a lemma saying that if you have a simple polygon with n vertices, you do not need more than n over 3 cameras. If you have an n-gon, that's the maximum number of cameras, actually floor of that. Floor of n over 3 is the maximum number of cameras you ever need. If some company comes here and says that, oh, I have a solution for you, we will be, if you have an n-gon, we will be needing n cameras placed at every vertex here. That's a really inefficient, very expensive solution. You don't need more than n over 3 cameras. We'll first prove that, and then this chapter we are going to subdivide this simple polygon into convex patches, and the simplest convex patch will be a triangle, and we will be doing this by drawing diagonals. For example, this is a diagonal. The line segment that connects two vertices will be a diagonal, and a valid diagonal will be a one which doesn't intersect polygon edges. So there's a question: are we assuming that? Yeah, we assume that the camera, unlike this one, for example, this camera, it has a field of view like this, but we will not assume that. In this problem, we assume that the camera sees, it can rotate around itself on this z-axis, and it will be able to see 360 degrees around it. Okay, so that's what we assume in this problem. We assume every camera has 360 degree field of view vision, and then so what will happen is that we are going to we will be drawing diagonals, as I said. For example, if you draw these two diagonals here, this is a triangle, this is a triangle. After we have this is going to motivate the problem of polygon triangulation, and after we have some kind of a triangulation of this polygon, what will happen is that we will be placing cameras on special locations of these triangles. We will actually be using adjacency of triangles as well. So by by solving a coloring problem of triangles, we will be placing n over 3 cameras. So this is another example. We will talk about the details of this problem and how we triangulate a polygon efficiently. These things we will cover in the upcoming weeks. But just for now, I'm just talking about this to indicate it's an example problem. So how we deal with these things. So let's get back to so I have a cat here that is bugging me. So from time to time, you may, when I'm doing the lectures at home, you may have some cat visitors as well. All right, so let's get back to the table of contents. Yeah. So yeah, we will be covering chapter 3. We will cover chapter 4, which is also a very nice problem. It's about linear programming, but the two-dimensional version of linear programming. Linear programming is used in operations research. It's optimizing a linear set of constraints we are given some linear constraints, and we have some variables, and we have an optimization function to optimize. So we try to assign variables to these. And what we will be doing is that we will be solving a two-dimensional version of this, which will be a geometric problem. Okay, and then we will talk about chapter 5. We will also cover chapter 5, in which we are going to talk about some data structures like KD trees and range trees, which will allow you to make windowing queries. So let me open this one again. So let me get a new page. So we will have points on the 2D plane and a windowing query if you have many of these points. So in general, in databases, this may be a multi-dimensional database. I mean, this is 2D, but imagine you have n-dimensional database. These points may be living in n-dimensional space. An orthogonal range query is a windowing query like this. If you have a window orthogonal rectangle, in which the sides are parallel to the x and y axis. This is what orthogonal range query means. I have x-axis here, y-axis here. This is an orthogonal range query. So given these points, and if I have a query like this, which points are inside this query box? And the linear solution to this, checking every one of your points in your database to see whether it's inside this box or not, is very trivial. Again, the exhaustive search or the first solution that comes into your mind is very simple. There is nothing geometric about this. I mean, trying to figure out whether a point is inside the rectangle or not is just a single if statement. If its x coordinate is between this and that, and if its y coordinate is between this and that, then it's inside. All right, so it's really simple. But now we will be asking, is this linear search optimum? And the answer will be no. We will be try to do this problem in sublinear time. In log n time, if I have n points, can you solve this query in all log n time or all square root of n time? So we will be looking for sublinear solutions. This is what the KD trees and range trees are about. This indexing your database to solve it in a better way. And in point location, we are going to cover this chapter as well. We will have a data structure named trapezoidal maps, and we will also solve the Voronoi diagrams problem. So chapter 6 and 7, we will cover those. We will cover chapter 8. As you can see, we cover most of the book. Chapter 8 is really nice. We will talk about the computer graphics problem in ray tracing, super sampling in ray tracing. How do you generate random points? For example, the problem, let me just talk about the problem in super sampling in ray tracing. Let me get a new. So super sampling is, if we have a pixel, imagine this is a pixel. In regular ray tracing, we shoot a ray at the center of this pixel. I mean, I have zoomed in this pixel a lot, so this is a single pixel. You have thousands and maybe millions of these pixels. If you, for example, if you have a 1 megapixel image, it means that you have 1 million pixels. And this is one of those 1 million pixels. In ray tracing, we shoot a ray from the focal point, from the eye point, to the center of every pixel, to the center of this pixel. Okay. Now, super sampling. I mean, if you have a low resolution image, the boundaries of your objects are going to appear zigzagged. Okay, so there will be some jittery. I mean, they will. And we also ask the question whether this ray intersects with the object or not. So if your resolution, if your number of pixels is not that many, you will have some zigzags at the boundaries of objects. To overcome this, one solution is to increase your resolution. You may just divide this into smaller pixels. Another solution that is used in maybe some earlier ray tracing applications is called super sampling. Instead of just using the center of this pixel, why don't we just randomly send rays to select some random points from this pixel, like 1, 2, 3, 4, 5, 6, and shoot the rays passing through these random points. Now, the problem that we will be solving is this. If I give you a pixel And if I give you a random set of points, okay, now consider these two sets. I have 7 points here, 3, 4, 5, 6, 7. Okay, look at this random set of points and look at this random set of points. You will immediately see that the second set is better, right? I mean, this one is not a very good random set of points because the entire lower right part of the pixel, there are no points in it. So in chapter 8, we are going to try to solve this problem. Given a set of random points in a square like this, which one is better? Is this a better random set of points inside this, or is this a better one? So otherwise, we will try to solve it, we'll try to maximize this. Can you find the line segment that passed through this pixel such that all of the points are to one side, and in this other side there are no points at all? I mean, we'll try to maximize this area. And if this area is large, it means that this is a bad sample, all right, bad set of random points. For example, you cannot do, if you try to draw a line here, the maximum area that you can cut off maybe is this part with empty size. Okay, so this is a really nice, interesting, I mean, the motivating problem of this ray tracing problem immediately became some interesting geometric problem. And in this chapter, we will be solving this. It became an optimization problem to solve. Okay. So this is what chapter 8 is. All right, let's go back to the book. We will not cover chapter 9 because chapter 9 is closely related to chapter 7. Voronoi diagrams and Delanoid triangulations are dual problems. I will just say to solve Delanoid triangulation of a set of points, just find the Voronoi diagram, take its dual, that's your Delanoid triangulation. So the solution for we will skip chapter 9 entirely. And then from chapter 10, we will talk about, we will cover chapter 10, interval trees, priority search trees, and segment trees. We will skip chapter 11 entirely. We will not talk about three-dimensional convex cells. And also BSP trees, we are not going to cover BSP trees. So chapter 11, 12 are skipped. And we are going to cover chapter 13, robot motion planning, skip chapter 14, and finally finish with chapter 15. So visibility graphs, computing the visibility graph of floor map with concave or convex obstacles will be our final problem that we will be discussing. And for all of these, as I said, we will be discussing some advanced algorithms. Some of those algorithms will be iterative, incremental. Some of them will be divide and conquer algorithms. Some of them will be randomized algorithms in which we will talk about expected complexity. So that may be something new. It's not average complexity. Average complexity is maybe different, or we will not talk about worst case, best case. The expected complexity is going to involve some statistics, some probability actually in its analysis, and we will talk about this in randomized algorithms. Okay, so chapter 16 is skipped as well. So in total, we skip 1, 2, 3, 4, 5. So we skip 5 of these 16 chapters, and we will be covering 11 chapters from the book in this 14 weeks of classes. Okay, so this week the book does not contain any geometric preliminaries that you may need. For example, the book just is going to describe algorithms at a very high level. If you go to the line segment intersection problem, for example, let me just quickly go over there. I just want to show you an algorithm. How it's described in the book. Yeah, for example, algorithm find intersection. As you can see, it's really high level in pseudocode. So initialize an empty static structure, determine the next event point. So inserting, deleting from some data structures. If you look at this handle event point, function, it says find the intersection. So how do we find the intersection between two line segments? It doesn't deal with, the book does not deal with this low level geometric operations. And it doesn't describe it at all, but you will need those if you want to implement this algorithm. So the algorithm as described like this is not very easy to implement. You need to implement these small details, and sometimes those small details may be really important. And for that, I'm going to provide you, the first week I'm going to spend with these geometric preliminaries, and I'm going to also provide you a material that I get from a competitive programming textbook. So chapter 7 of this competitive programming textbook, the name of the book is Competitive Programming 3. It's also known as CP3. So CP3, there is also CP4 version is also, it came out. And in this one, since it's targeted towards competitive programming, it has really low level description of code. Starting with points, lines, polygons. So it's really useful. So I'm going to share this PDF with you as well. So yeah, that's the material. If you go back to now syllabus related material, go to the course website here. The book and it's this preliminary geometric material PDF is also available. If you go to the schedule section, the schedule section, there is a hidden folder here underneath, which is this schedule book. I'm going to paste it in chat box. All right. So if you go there, you will be greeted with a. I already entered the password earlier. You will be prompted with username and password. And the username I'm writing in the chat box is CENG570. This is the username, and the password is 5710773 underscore. Okay, so with this username and password, you will be able to access this copyrighted material that I have put here. You have the PDF of our textbook, and also this preliminary geometric operations PDF that I show you is also available here. You can use this one. All right, so before we go into break, let me talk about other material. Like we are going to have 4 assignments. I plan to have 3 of them written assignments, 1 of them programming. Each of them are going to be 8% each, totaling 32% of your overall grade. We will have 1 midterm exam, 33% worth, and 1 final exam, 35% worth. I plan to have both the midterm and final exam as take-home exams because I will not really bother about cheating in this course because this is a graduate level course, and really the GPA in a graduate for a master's student or a PhD student, the GPA is really not important because nobody looks into your GPA when you apply for example, PhD or postdoc. The actual output of a graduate student are the research, are the papers that a grad student produces. So GPA really, your undergrad GPA is really important. That's true, but a graduate level GPA is not that important. So I will really not bother about cheating or not. So my real goal is just for you to learn these advanced algorithms and data structures in this course. So I will just leave you free in the midterm and final exams and the written and programming assignments as well too. So I hope it will be just a fun experience to talk about these algorithms and data structures in class. Okay, so since this is a graduate level course, as I said, I will not. I mean, it's many of you could get AAs. That's okay for me. I already give high grades to many of the classes I teach. All right. So what I'm trying to say is, getting a good grade should not be your main motivation. Okay. Your main motivation should be to have fun, to learn these interesting algorithms and data structures that may be useful to you in your research, or maybe just as a hobby, or if you're working, maybe you may face a problem at work about some geometric problem, and the techniques we learn here hopefully will be valuable in that regard. All right, so I will be using odtuclass to post the videos. Actually, for last night's lecture, I already have the videos. I'm just going to post them like this. Right now, I'm doing a post to section 2, video links for yesterday's lecture. There is a nice website called the Computational Geometry Algorithms Library. Some of the algorithms that we are going to discuss in this course, they're already implemented here. So if you want to practically use these algorithms in your research or in anything you are going to pursue, you may also take a look at this Computational Geometry Algorithms Library, cgal.org. I'm also posting it in the chat box. I haven't used this cgal library myself, but I know that it's very popular in the area of computational geometry, and it's used by many people. All right. I may have the announcements on odtuclass. And odtuclass announcements will be you will be notified by email. So every time I post the announcement here, I select this option saying that, I mean, this is a really bad user interface, by the way. Look at this. Send forum post notifications with no editing time delay. I have no idea what this sentence means, but it just means that you're notified by email if I click this box. I mean, it could have just said send email to participants. All right, so this is what it means. So I click this box every time. If I don't forget it, I click this box, which means that every announcement I make on course website, you will be notified by that. All right, so which means that check your meta emails regularly. All right, so I think that's it for syllabus related material. We are going to have like 10 or 15 minute break. I will start at around 13-minute break, 10:40. I will talk about geometric preliminaries. I will go over the first week slides, and I will talk about points, vectors, some vector algebra, dot product, cross product, how cross product is useful to us in many applications. I will show some applications of cross product, and I will talk about some distances, lines and line segments. I will leave this part, maybe planes, half spaces, or circles for next week. So after the break, we will have another 1 hour or so. Okay. Oh, okay. So that's so it's somebody. If that box is not checked, odtuclass gives you time around 30 minutes to edit your post before notifying students. Oh, okay. Oh, so even if you don't check the box, it's always notified. So I understood the meaning of that box incorrectly. Thank you for clarifying that for me. I thought that box was there to send an email. So an email is sent anyways, even if I check the box or not. Okay, so that's good to know. Thank you for the clarification. Yeah, after the 10-minute break, I will talk about the geometric preliminaries. Okay, and half of those geometric preliminaries, I will leave the remaining half for next week. So let's, do you have any questions about syllabus related material? All right, I guess no questions. So see you in 10 minutes. I will stop this recording, and I will also stop the meeting.